So the interrupts of 8085, as you know that Intel 8085 has 5 interrupts, namely trap, RST 7.5, 6.5, 5.5 and INTR. And out of these interrupts, trap is having highest priority, and then 7.5, 6.5, 5.5 and then INTR. So INTR has the lowest priority. Now any device who wants to interrupt the processor, the first and the foremost requirement is to enable the interrupt flip-flop. Until unless the interrupt flip-flop is not enabled, no device can interrupt the functionality of 8085 processor. So meaning thereby, if we want to use these 5 interrupt lines, and through these interrupt lines the devices are connected, and the device wants to interrupt the processing of 8085, it is must that the flip-flop which is related with the interrupt must be enabled. And this enabling of interrupt flip-flop is done by instruction, and that instruction is known as EI, in enable interrupt. Whenever a EI instruction is used within the main program, at that moment of time after the execution of that instruction, the flip-flop will be enabled and the microprocessor can be interrupted by any device which is connected through these interrupt lines. Similarly, when we want that no device can interrupt the processor, in that case, we have to disable the interrupt flip-flop. And that can be done with the help of instruction, that is DI, disable interrupt. Now the non-maskable interrupt is exceptional case. It cannot be enabled, it cannot be disabled, it is enabled permanently because of having the highest priority. It cannot be disabled, but rest of the interrupt can be enabled or can be disabled. Now what happens when an interrupt is received by a processor? Whenever any device which is connected to the processor through these interrupt lines interrupts, sends a high signal on the interrupt line, and this interrupt is received by the processor. At that moment of time, processor might be doing something. So what processor will do after receiving the interrupt signal? It will complete the execution of the current instruction. First of all, it will complete the execution of the current instruction which is in progress, and immediately it resets the enable flip-flop, interrupt enable flip-flop, because of the reason that no other device can interrupt the microprocessor operation. So before and after that, when it receives, it completes its execution, then it resets the interrupt enable flip-flop, and then what it will do? Then it will execute then it will execute the interrupt service subroutine, which is meant for that particular device. So that interrupt service subroutine is called ISS. Now this service subroutine is already written somewhere in the memory, having some memory location. Instead of executing the next instruction, what it will do, it will execute the interrupt service subroutine. And what is in the interrupt service routine? Interrupt service subroutine will contain certain instructions which will be helpful in transferring of the data So before it is going to execute the interrupt service subroutine, it will first reset the interrupt enable flip-flop so that other devices cannot interrupt the processor. Now this resetting of the interrupt enable flip-flop can be done in 3 ways. The first way of doing the resetting of the interrupt enable flip-flop is by including a DI instruction within the program. Second way by which it can be disabled is while the processor is entertaining one device which has interrupted, it automatically going to reset the interrupt enable flip-flop. And the third way of resetting the interrupt enable flip-flop is by doing the resetting process of the microprocessor. So these are the 3 ways by which this resetting can be done. Now, as far as the masking is concerned, as I told you that RST 7.5, RST 6.5, RST 5.5, INTR, all these are maskable interrupts. If I say that these are maskable interrupts, meaning thereby masking means they can be avoided for a few times. They can be entertained, but they can be avoided. They can be delayed. The processing of those interrupts can be delayed. And this masking, even though we can mask the individual interrupt line also, and this masking can be done through the program or the instruction. So this is the detail about the interrupts which are used in 8085. Now, we have 2 categories of interrupt, maskable and non-maskable interrupts. Trap is a non-maskable, and it does not require any kind of enabling of flip-flop or disabling. It always remains available for the processor, and if any device has interrupted through this trap line, the processor has to entertain it. And this trap line is not accessible to the user also. And most often it is being used in the emergency situation, such as power failure. For example, I can give you one more example. If you take an example of a sugar mill contains, there are many machines which are being used, huge machine. One of the machine is the boiler. And boiler, we have to maintain a certain, and suppose that all the control system is being controlled by microprocessor based system. And we have set a temperature of the boiler, and the temperature of the boiler should not increase more than 360 degrees. And this is mechanized by a computerized system. And now suppose at a particular moment of time, because whenever the temperature of the boiler increases, it may cause an accident, it may cause a failure. So for that particular purpose, if by the way, due to some mishandling or due to some way, the temperature of the boiler is going to increase. So what we have done, we have set a target that should not increase more than 360 degrees. Whenever the temperature of the boiler become more than 360 degrees, immediately the power should be shut down, so that the the increase in the temperature is not going to cause any kind of damage. So for that particular purpose, if the temperature is going to increase more than, we have a sensor which will be sensing the temperature of the boiler. And if it is going to increase more than 360 degree, it is going to trap, it is connected through a trap line of the microprocessor based system and going to shut down the system overall, so that the situation with which the damage can happen should not. So it is normally used in the emergency situations. Now the interrupt, as I told you, the maskable interrupts 7.55. If we want these interrupts to be ineffective, we don't want any device which is connected with RST 7.5, we don't want that device to interrupt the processor. We can do it by writing a program, by using certain instructions. We want RST 7.5 should not, the device which is connected through RST 6.5 should not interrupt. The device which is connected through RST 5.5 should not interrupt. So meaning thereby, by writing a certain instruction in the program, we can disable, we can mask the RST 7.5, 6.5, and 5.5, because these are the maskable interrupts. And as I told you, this masking of the individual interrupt or more than one interrupt or all the interrupts can be done with the help of writing a program or the instruction. Now, what is hardware interrupt and what is software interrupt? We have another category of interrupt, that is hardware interrupt and the software interrupt. Now, whenever there is an interrupt which is caused by any input-output device, that is called hardware interrupt. The normal operation of a microprocessor can only be interrupted by abnormal internal condition or by providing a special instruction. Such type of instruction, such type of interrupt is called software interrupt, in which we will be using a special instructions to interrupt the processing of the processor. That is called the software interrupt. So hardware interrupt is that interrupt which is caused by an input-output device, and software interrupts are those interrupts which are caused by writing an instruction. So it is called software interrupt. Now, if you take an example of a software interrupt, we have many instructions. While discussing the subroutine, I have given you the idea of RST instructions. And the format of using RST instructions are RST-N, where N is from 0 to 7. We have 8 RST instructions. And these RST instructions are basically software interrupts. When RST instruction is inserted in a program, we have put in the program, in the main program, the program is executing up to the point, up to the place where the RST instruction is written. And when it executes RST instruction, it will switch over, it will not execute the normal sequence. Whenever RST instruction is executed, it will switch over to a certain subroutine that is called service subroutine, which is written somewhere in the memory. And for each RST instruction, there are certain memory locations where the individual codes, instructions are written. Normally, the use of RST instruction is applied while doing the debugging of the program, as well as the internal abnormal or unusual condition which prevents the normal processing sequence of a processor are also called exceptions. For example, if anyhow while executing a program, we have come into the situation that is divide by 0, which is going to cause a problem, it is an exceptional case. One more important thing, that when several input output devices are connected with the INTR line, the external hardware is used to interface the input output devices. And these external hardware circuitry is going to generate RST codes to implement the multiple interrupt system. And how it will be done, we will be discussing later on. So this is about the hardware interrupt and the software. Now the software, the instructions which are used for making the interrupt. The first instruction is EI instruction, which is enable interrupt. And the second instruction is DI interrupt, that is disable interrupt. EI is a 1-byte instruction and it enables the interrupt process. The purpose of EI is to enable the interrupt process. Once it is going to enable the interrupt process, any device which is connected with the microprocessor can interrupt the operation of microprocessor. As well as it is written that it disables the interrupt process. Now it disables the interrupt process since it enables the interrupt process, and whenever interrupt processes are enabled and any device has interrupted the operation of microprocessor, and microprocessor is going to handle that device which has interrupted, it automatically disables the interrupt process. So EI is going to enable the interrupt process, but it is going to disable the interrupt process once any device has interrupted it. That is why both the things are written. However, this seems to be contradictory, but it is enabling, as well as once it receives any signal from any device who want to interrupt, it disables the rest of the process. And second instruction is DI. DI means disable the interrupt. This is again 1-byte instruction, and the sole purpose of DI instruction is to disable the interrupt process. And once DI instruction has been executed, any device which is connected to the maskable interrupts, any device which are connected to the maskable interrupt lines cannot interrupt the operation of microprocessor. But once we write EI, any device which is connected with the maskable interrupt line can interrupt the operation of microprocessor. Now, DI instruction is normally used to disable the interrupt process, and it is included in the program when we want that no other device should interrupt the operation of the microprocessor. So it depends upon the requirement. But these two instructions are used for exploiting the interrupt process in 8085. So now let us discuss the RST instructions. As I told you that RST instructions are the software interrupts. And whenever we use that, the normal sequence of execution of the program will not happen because it will become a part of the main program. And up to RST instruction, it will execute. But after RST instruction, it will not execute the next instruction. Then what it will do? It will execute the service subroutine, which is written already in the memory and depends on the RST instruction used. There are 8 number of RST instructions, RST 0 to 7. And the hex code of each instructions are this. And the call location of the, if RST 0 is written, it will go to this location where the program is written. If you have written RST 4, it will go to this location where the separate program is written. Now this These instructions come under the instruction sets of 8085. And these instructions are single byte instructions. And the purpose of using this instruction is to transfer the program execution to a specific location on page 00. Page 00 having different location 00, 08, 10, 18, 20, 28, 30, and 38. RST instructions are executed in a very similar fashion as we execute the call instructions. And whenever RST instruction, what happens when the call instruction is executed? Whatever is the program counter content, which is the next instructions address, it is stored in the stack, and then it will move to the subroutine. Similarly, whenever RST instruction is executed, whatever is the content of program counter, it is saved temporarily in the stack. So the address of the program counter, which is the address of the next instruction after the RST instruction, is stored on the stack before the program execution is transferred to the RST call location. These locations are called call locations. When the processor encounters a return instruction in the subroutine associated with the RST instruction, the program returns to the address that was stored on the stack. So whatever is content of the stack, it is taken back into the program counter, and then normal execution starts. This is the case of software interrupt. In case of hardware interrupt, we have to use an RST instruction to restart the program execution. In that, you have to do it. So these are the certain ports, and these are the call locations of the different RST instructions. Now, these RST instructions are associated with the INTR interrupt. So you can say that there are 8 numbers of call locations for the INTR interrupt. And this figure shows that what are the different call locations. For INTR external hardware, for INTR instruction, external hardware is used to transfer the program to a specific call location. The hardware circuit generates RST code for this particular purpose, and the INTR line is sampled by the microprocessor in the last state of the last machine cycle of each instruction. When INTR line is high, the microprocessor saves the content of the program counter onto the stack and then sends an interrupt acknowledge signal to that particular external device. In response to that interrupt acknowledge signal, the external hardware circuit, hardware device is going to generate an RST code. And when the microprocessor receives this code, it transfers the program to the corresponding call locations. So we have up to 8 numbers of the input output devices which can be connected through the INTR lines through an external hardware. And priority can be assigned to the input output devices connected to the INTR line through external hardware or with the help of interrupt controller. What is the role of interrupt controller? That we will be discussing later on. This external hardware is going to recognize which input output device has interrupted, and it generates correspondingly proper RST code that causes the microprocessor to take up the ISS for that particular input and output device. And this external hardware can be built by employing the priority encoder and a tri-state buffer or priority interrupt controller. Now, what is the role of programmable interrupt controller and how it works? We will discuss it later on. Then we have interrupt call locations. When an interrupt occurs, the program is transferred to the specific location that is explained earlier also. Then the monitor transfers the program from the specific memory location to another memory location from where the user can write the program for the interrupt service subroutine. For trap, for RST 7.5, for RST 6.5, RST 5.5, program is automatically transferred to the specific memory location, that is 0024, 003C, 0034, and 002. Whenever any device which is connected with RST 7.5 is going to interrupt the process operation of 8085, it automatically transfers its control to the 003C memory location. But if any device which is connected through the INTR line, that device will not directly transfer it to the call location. That device is being acknowledged by the processor that you have sent an interrupt and it is the acknowledged signal. Once the device is going to receive the acknowledged signal, that hardware device will generate one of the RST instruction and gives it to the microprocessor. And depending upon that RST instruction, it will go to a certain call location. So this is how it's working. So that is why for RST 0 to 7, we have different call locations. Similarly, for trap and RST 7.5, we have different call locations. And all these call locations are summarized in the figure, this one. If any device which has interrupted through INTR line, this can move to 000, 0008, 0010, 0018, 0020, 0020B, 0030, and 0038. But whenever any device has interrupted through RST 7.5, it will move to 002C. Whenever any device has interrupted through RST 6.5, it will move to 0034. Any device has interrupted through RST 7.5, it will move to 003C. And any device who has interrupted with trap, it will move to 0024. So these are the certain locations where subroutine has been written called interrupt service subroutine to handle which interrupt, which device has interrupted through which interrupt. And every location is different and every program is different depending upon what type of operation it's going to perform. Let us discuss all this circuit also. Now here we have an interrupt enable flip-flop. This interrupt enable flip-flop can be set, means Q output will be high if enable interrupt is high. It means it is must that interrupt must have been enabled. This is a simple RS flip-flop and it can be disabled by 3 operations: by using DI instruction, by reset, or any interrupt recognized. Once any interrupt is recognized, it is going to disable the interrupt. So set can be done, means Q will be high if EI is high, and rest of the cases Q will be low. Whenever Q will be low, this AND gate, this AND gate, this AND gate, and this AND gate will become low. The output will become low. It means it will not transfer to individual memory location. Meaning thereby this, all these NAND gates to become active to give output 1, it is necessary that Q should be high. Q should be high. But to enable this AND gate, it is also required that interrupt line should be high. So it means until unless these both lines are high, then only the RST code will be generated and it will be going to execute the service subroutine. Similarly, this AND gate will be giving the output high when all these 3 inputs are high. How these 3 inputs are high? Meaning there RST 5.5 is enabled, this interrupt enable flip-flop is enabled, as well as the masking is 0. If the mask bit is 0, it means here it will be 1. So it means 1, 1, 1, it will give the output 1. Then only this location will be fetched and executed. Similarly, 6.5 masking, it should not be masked, so it will be 0. So it means here it will be 1. RST 7 6.5 line should be high, as well as enable interrupt enable flip flop should be high. And similarly with the case of, so this is the total illustration of how this vectored interrupt. Now all these are vectored interrupt because it is being vectored. The locations are vectored. That is why it is called the vectored interrupt. Every location is different, but it will activate when and only when EI is high. If we want to activate this, INTR line should be high. If we want to activate this, RST 5.5 should be high, and so on. And you see, trap does not have any. It has to handle, if trap is high, it has to handle 0024 memory location where the subroutine, interrupt service subroutine for the trap is written. So that is all about the interrupts of 8085.